last but not the least, Dr. Lance Fiondella. The title of his presentation is Covariate Software Vulnerability Discovery Model to Support Cybersecurity. Lance Fiondella is an associate professor in the Department of Electrical and Computer Engineering at the University of Massachusetts, Dartmouth, and the founding director of the University Cybersecurity Center. Most of his project and research has been funded by DHS, Army, Navy, Air Force, NASA, and National Science Foundation, including a Career Award and CyberCorps Scholarship for Service. Welcome, Dr. Fiondella.
So I know, yes.
Just wait, I'm waiting for the slide.
Okay.
I think it's over there.
I will stand here so the online audience can hear me. And since I don't know who's in the audience, I'm just going to say things I probably shouldn't. Okay, and I have to look up here to, do I get a clicker?
Yeah, there's a
This is a clicker.
forward.
Yeah. Okay, I see my slides now. Thank you. So I don't have any fancy whiz bangs. I'm a college professor. You know, folks in DoD, NASA, all those, you get to, you know, either hope things don't blow up or blow things up. But what I've been trying to do here is create some effort data to demonstrate the applicability of these models, which were produced as part of the project, the NSF project, to test and evaluation, specifically the software vulnerabilities or the software reliability issues that also are within the subset that belong to cyber test and evaluation. So ultimately, here's a tool. This is not NIST RMF. This is not MITRE CWE or CAPEC. It is, you know, like I'm just a college professor. They have millions or billions, but hopefully this is that quantitative complement that everybody's been dying for and can be used for T&E of software-intensive systems across the department and across the government in general acquisition. All right. Oh, gosh. Should have reviewed my slides before, huh? All right. So, you know, preaching to the choir, doom and gloom. We know that software enables national security, defense, and pretty much everything we take for, you know, granted in our modern society. The short story is that, you know, software reliability growth models like Kazu was talking about, we talk about defect discovery, we talk about the lagging curve of defect resolution, and you really better tell me when I'm going to run out of time, okay? So thank you. But ultimately, you know, they've translated this into, well, we've done this for defect detection. Let's talk about defect detection, not defection, that is relevant to vulnerabilities. So discover the vulnerabilities, close the vulnerabilities. It's that time between discovery and closure that is where we're vulnerable and also where we would want to essentially be able to do the same kind of red teaming against our adversaries to know when that window is, when, you know, an opportunity we can strike or essentially our window of opportunity closes. So they're both defensive and offensive, you know, capabilities within this kind of assessment technique. It's just stochastic processes, not capability engineering that we all care about, but it's that T&E capability that we need to inform not just release decisions, but operational decisions as well. But when I talk about taxonomies, techniques, and tools, so I think, you know, taxonomies are those things like, you know, the RMF of here are bad things, don't do them, whether it's in the case of software or now AI, whatever that means within the software or systems world. And then there are techniques. So I think of these as the PhD level publication published in a journal. And then there's the tools, that is the physical implementation. So, you know, Kazu's work is a tool implementation of those techniques. But what's missing here, right? What's missing here is the ability to, from an architectural standpoint, come up with a rigorous test and evaluation strategy. That's that test and evaluation master plan. That's, you know, in whatever document to inform what should we be testing. So yeah, sure. Okay, CWE is this great laundry list of all the hardware, software, and human factors, ways we can get to the system for security, but what's relevant to my specific system? Sure, you know, digital engineering, automated failure modes and effects analysis is going to just spit out this master tester plan, give us a big software and system testing plan, or our adversarial machine learning, whatever, right? That's our next generation effort, is showing the relevance of these models. In fact, one of my students talked about this in his speed session, is, you know, demonstrating the applicability of these models to test and evaluation of machine learning components within machine learning enabled systems, as I call them. All right. So where am I all going with this? This was just a big effort to demonstrate to government especially, and the labs that support them, the FFRDCs and UARCs, that it doesn't cost millions to collect data. Don't let your program manager scare you away, because if I can do it on a budget, for a master's student, you can do it with your government budget. That's my simple, what I hope you can take away and push back against program managers who say, oh, I can't do it. That's a lie, right? And don't let your contractor scare you off either. That's just a lie. So again, let me just acknowledge the sponsors up front. National Science Foundation supported the modeling, but Air Force Institute of Technology's Homeland Security Community of Best Practices supported the specific application, the case study to cybersecurity test and evaluation. So, and that was with DHS T&E money. So thanks to them. Long story up short, there are these parametric models that essentially don't consider the multiple activities, right? So you think if, as Kaz was saying, test effort. Well, we collected multiple types of testing effort. And in this case, testing effort was the different types of penetration testing activities performed to discover vulnerabilities within that specific software. Not all glamorous like those, complex systems that you're dealing out there in the acquisition community, but something simple enough to demonstrate the proof of concept of here are the steps you want to take. And this is published in the International Symposium on Software Reliability Engineering. I'm happy to share it with you if you don't have the ability to access the subscription. So, if you want to learn more about this, grab the slides. My contact information is there. Happy to share the full manuscript. The tools are free and open source, all the way down to the source code, so you can get it through your IA and you can tell your contractors to do the same. So there's no excuse not to do this, and data collection is feasible. If a experienced PhD student who has real world experience doing penetration testing can mentor a master's student to do it, surely any major acquisition program can do it as well. But ultimately what we did was we showed that by collecting, so what we did, collect a web app, identify a target, right? We don't have a weapon system. We don't have a major information system. We're not dealing with systems within the intelligence community or you name it. What we did was we got a web app, right? Because that's the low-hanging fruit, and demonstrate broad applicability. Ultimately, my hope with this study is to inspire the defense and government acquisition community in general that's focused on T&E to adopt these methodologies, not because I want a model named after me to be immortalized, but because I want to be of service to the T&E community. And in doing so, show that these steps are possible. So we identified a web app because that's what we can do in the unclassified space. That's what the learning, like the hack this system to get your credentials or get this certificate. And we identified the most realistic one. It was some kind of juice shop. It was basically an e-commerce web app, and we poked and prodded at it. We recorded the amount of effort expended in each of multiple discrete intervals, and that was our effort data that we collected. And what we ultimately showed was that these models that are essentially discrete multivariate time series that use the Cox proportional hazard model on top of the non-homogeneous Poisson process can more accurately predict into the future. Unfortunately, the parametric curves are disastrous. Because ultimately, if they impose a structure and essentially some kind of decrease in the number of future defects discovered, there's no way in where that you're ever going to be able to say, well, what happens if you do the release and the nation state actors throws their supercomputer power at this to try to penetrate your system? It just cannot accommodate it. Whereas you can talk about those CPU cycles as a column of your covariate data for the effort exerted to identify that vulnerability. So in that regard, the previous generation, I literally discouraged the use of our lab's previous generation models because they lack this capability. So I'm encouraging the use of our most recent products and tools, which again are free and open source. But ultimately, we showed that not only can we more accurately predict, there are certain structural flaws in the previous legacy generation models that should simply be not used. And what troubles me most, well, lots of things trouble me, but that, never mind the existing contracting structure that prevents, after the contract is put in place, the ability to collect this kind of data, the widespread lack of adoption of even previous generation tools that are, in my opinion, now inadequate and perhaps never were. So, this was the setup. It was just a virtual machine. The student learned, got a Linux box and attacked their juice shop. Because that's what they could do. So it's an e-commerce website where you're in the city and you're going to go order your bubble tea or whatever the heck it is. I don't know what get deliveries at lunch because you're too busy, eating in front of your laptop miserably, like everybody does these days, I suppose. And I'll be the first to acknowledge this is not, but we did map to MITRE CWE as well to show that for especially the DoD community and national security community, what we did was we just took Open Web Application Project top 10 vulnerabilities. So these are the top 10 vulnerabilities. Can you tell me how much time I got left? All right, I'm going to talk fast. We might even travel time. But this is not even 100% of all the things that can go wrong with a web application. They're just the top 10. And this is reported by literally hundreds or thousands of web administrators across the world. It's open, meaning they share. These are the things that are the biggest problems. So you have, programmers don't know how to code libraries that do cryptography. Not only that, they don't even know how to call the functions properly to make the cryptography work properly. So that cryptographic failure, category A2, is an example of just the programmer did it wrong, right? It's a design flaw. You can have security misconfigurations, you can have failure to patch, you can have all these, but these are just top 10, right? And so, well, like I said, CWE is this massive enumeration of all the bad things that can happen. Are they even relevant to my specific system? Well, without that, like digital representation of my architecture, how would I know, right? What tests should I do? But like I said, at least this is starting to show that we could predict a big class of get rid of the whole low-hanging fruit, because we know getting rid of the low-hanging fruit is at least going to raise the bar on what our adversaries and which adversaries could even touch us in those systems. And so what we did was we essentially identified 3 tools. They are our 3 covariates in the statistical model sense. And we categorize, so there's Z-attack, proxy, burp suite, and then manual testing. I want to get down into the details of this table, but one of the most important things to realize is that, remember, a lot of penetration testers can't even code. They can't build hardware, they can't build software. All they can do is point and click to use what capabilities are enabled in their pen testing tool suite. They don't have degrees in computer science or computer engineering or the sciences of building these systems. All they know how to do is point and click and read the script. How is that an exhaustive test methodology? Do we want to be employing that in our contractor base to rigorously test our systems? Absolutely not. So the point is that these tools are good, Z-attack, proxy, burp suite, but there's also manual testing. That's the third of the 3 covariates that are out there. And so this is our data set. Like literally, I joked, like, if I could do this on a budget for a master's student, surely the United States government can do it for our critical national security programs. And what we did, I wish this had a laser pointer, but we've got 8 intervals. K is the number of vulnerabilities discovered in each of those intervals, and A1 through 10 are the decomposition of what class of those top 10 the category fell into. So the student was very meticulous in essentially taking that extra time, instead of just saying, listen, kids, I know you all want to be, machine learning people and cybersecurity and hackers someday, but for gosh sake, we also need to measure how well we do this. So statistics and the mathematics that goes into test and evaluation, the quality assurance on top of building it, but also breaking it and rigorously assuring it is very important. So that little bit of extra effort for the student, she first had to learn how to do penetration testing. She then had to also learn how to document it properly. Imagine that. Write that into the contract. Make it happen. Okay, so she was able to break it down into the 10 categories. So for example, row 1, there were 2 in the first of the 10 categories and 1 in categories 4 and 5, whatever they are, right? Go look them up. And you could do this for MITRE CWE with their hundreds of, whatever the, categorization and taxonomy they've got there, and they're doing another one, I'm sure, for AI, but I don't see it in the public literature, so I imagine it's more carefully guarded at this point. But those last 3 columns are the number of seconds spent. That's the effort data. So maybe, Kazu, you want to throw this into your tool and see what kind of results you get, right? Can you predict better? Are we finding the vulnerabilities because of these effort data? Can you handle multiple levels of effort? And so what you can see is the response. It's a multivariate, essentially it's a single response. That is, how many vulnerabilities did I discover as a function of what was I doing? Like I say, I used to have, there was a good joke about the monkey, the bus driver, and the police officer, and they map to different people within the T&E ecosystem, but I'm not going to tell the joke. We can talk about that at the poster session, okay? But ultimately, the question is, who was doing what At what time shouldn't that be able to tell us what tools are effective? Because, so in this regard, this is a framework. This is not a specific, like, mine is better than theirs. Every lab, they've got these massive budgets. They say, hey, we've got the bleeding edge, and they like to brag when they score a point on another lab who, they broke their system and say, yeah, we beat, say, Lincoln Labs or APL. And, there's that friendly competition among the labs. But what I'm more concerned about is saying, well, which of these tools in combination is most effective? And that's ultimately what the government or the acquisition authority is concerned with. And can we not add a column 4, which is that new next generation tool? How does it overlap with the existing 3 tools? So in that regard, big vision here on what those columns could constitute. Those could be the exquisite capabilities within the red teaming community, within the national labs and the government, that are ultimately the test techniques, not a master's student learning how to hack with, essentially kiddie script capability and a little bit beyond, because the second author is has industry experience. So hopefully there's something of value you can all take away here, both in the room and online. I'm not going to do the math. So ultimately, we care about how many vulnerabilities we're going to detect. We care about, what's the probability of detection given a level of effort? And I guess I'll get into this a little bit. So I'll just talk about a few parameters. These X parameters, I want to speak in the microphone, are the level of effort. So if I back up, that's the matrix, the ZBM column. So we have X1, 2, and 3 in intervals 1 through 8. That's essentially the effort we're putting in. We could be doing one or more things. And the betas, the coefficients, are essentially the effectiveness, the relative, like, we could quantify the effectiveness of these 3 tools to expose vulnerabilities within this specific system. So our numerical estimates of, say, beta 1, 2, 3 for ZAP, burp, and manual testing will tell us per unit time how effective is this. We would expect it to be positive, because I would assume we will use tools that are positively associated with vulnerability discovery, not rain dances, voodoo, that sort of thing, that don't really have any relationship or an inverse relationship with finding the vulnerabilities within our system. So remember, the point of these software reliability models and software vulnerability discovery models when applied to security is, let's find it so we can fix it before we put it out there for our adversary to find it and take advantage of it, right? So that's why we have defect discovery and then defect resolution, and we care about closing the gap before release. But of course, that's getting harder and harder because of the push to do continuous deployment. So hence, further enhancing and increasing the need for the ability to close the gap faster than ever, because our adversaries are going to look for those gaps faster than ever. And so, essentially the probability of detection can be characterized through various, essentially, we're talking discrete models here, so we have discrete hazard functions. But the point is, we all know in the statistical community that no one curve characterizes all data best. So the typical approach is to apply multiple variations, or a wide range of models, and then see which ones perform best with respect to whichever combination of measures of goodness of fit and predictive capability that we're most concerned with. So we have a variation, we have various hazard functions that can be incorporated into the model. We can solve, we can estimate, we can do, and that's all automated, right? So the open source tool it lowers the curve. I mean, I've seen people with PhDs in software reliability, supposedly, who couldn't tell why the model couldn't predict. It's because the model didn't, we didn't solve the underlying optimization problem to fit the curve properly, among other things. So to drastically lower the barrier to entry to using the models, we implement the models in open source tools. So thank you very much, National Science Foundation, taxpayer. We give the model away for free, and go ahead and use it. Here's the source code. You can take it or leave it. Take out what you don't want. If you have the capability to put something in, be my guest. But what I'm trying to do here is compare why those parametric models are no good for understanding the fielded environment where the nation state actor may have massive resources to expose the vulnerabilities. Never mind the vectors by which they do that, technical at least. I'm not getting into the human factors here. But ultimately, it's just some big parametric model with, a cumulative, it's like a scaled cumulative distribution function. As time goes to infinity, we're going to find so many defects in theory. Assuming I stop adding functionality, we'll find and fix all the defects. I mean, those are strong assumptions, and you might get a defective distribution in the statistical terminology. But ultimately, why I'm showing that ugly equation 12 there with the cubic term in the numerator, 5 minutes, all right. We're rocking and rolling now. And I know I won't want to keep you from the poster session and your open bar, if it's open bar like it was last year. Yeah, somebody's eyes in the back just lit up. The point is look at this. This is going to show that increasing and decreasing curve and not much else. So like I said, I can give you data, and notice it's single variant, it's time. There's t, there's no x1, no x2, no x3, no way to incorporate the information on what the monkey was doing with the bus. Actually, who was driving? Well, okay, I'll give away the punchline. The monkey was driving the bus, okay? But the point here is we need to record, i.e. put on contract data, collect it, use it. I'm not saying immortalize this model. I mean, the Japanese colleagues, they produced a predecessor to this, so I have no claim to originality. I'm just trying to make it of use to this community in general. But ultimately, there's only unidimensional time, and therefore there is no insight into what of the penetration testing techniques, if we take the security application into consideration, are most effective. Remember also that fitted models can serve as the basis of optimization. So this can become a portfolio allocation problem in the, not Nobel Prize, but Swiss Bank Prize of, instead of planning for retirement and finding that optimal trade-off between risk and reward when it comes to my investment portfolio, here we can say, well, I've got beta 1, 2, 3. There is some underlying correlation structure. Maybe it's Fisher information, who knows? But ultimately, I want to know, I have only so many hours in the day. Believe me, I know that more than ever these days. How do I allocate my limited effort to my different penetration testing activities to maximize the number of vulnerabilities discovered so that I can send them back to the coding team to close those gaps so that we can release the most bulletproof piece of software for that system, essentially close the critical defects based on severity and so on. And remember, data can always be subsetted by severity, so often the question arises to say, well, can I just focus on a specific failure mode? Absolutely. In fact, I will say severity is a red herring. Don't waste your time with like severity level 1, 2, 3, 4, 5. Focus on what I'm advocating for is a much more fine-grained characterization of failure modes to the system and mission, because ultimately, if you can't do defect curves according to your mission capabilities, like shoot gun or navigate autonomously or whatever that capability is, whatever that software capability is from, again, we need to think about failure modes for machine learning as well. If we don't take a failure modes subsetting approach to this kind of software defect characterization, severity levels is a very blunt hammer that really isn't going to inform extremely detailed quantitative contracting that will guarantee these capabilities to the degree we truly want to. If I'm not being clear, please feel free to ask me questions. All right, we just had to do some routine mathematics to make the models comparison. Across the board, the covariate models perform better, both with respect to in-sample, out-of-sample, and information theoretic goodness as a fit that Kazu is giving trashing. So we're in friendly competition. And this one isn't so interesting, but this is how they show the data. Number of defects discovered is that step function, and you can't really tell the difference between the old model that's cited 1,000 times and our model, which is probably cited 2 times so far. But when you look at and I apologize, you can't see the bar chart behind, but that's the number of vulnerabilities actually discovered. What you see is that the dark curve, the black curve, that's the covariate model. It much better not only tracks the in-sample data, but predicts to say if I throw this much of X, Y, and Z type of attack method at my system, which I didn't use for model fitting, we can also predict better. So ultimately, that's why I'm saying the parametric curve that you get in the gray bar is never going to be able to characterize the threat in the field, period. Okay, so like I said, our ongoing efforts, it's collaboration with the Indian Statistical Institute in Calcutta. It's a very well-known institution in statistics. And that's a collaborative project through National Science Foundation and the DST, which is the NSF equivalent, ultimately trying to show the applicability of using multiple adversarial machine learning techniques, so the domain-specific attack techniques for machine learning enabled software and systems to demonstrate the utility of how can we do T&E for machine learning that ultimately informs what the failure modes are based on what the capability of the machine learning is enabling within that system. So we want, like across the department, you're saying like, yeah, we need some AI for this, this, and this. Well, what is the specific capability that the machine learning is enabling within that? What are the corresponding failure modes? Because the architecture is going to change. And ultimately, so there's a lot of system architecting that surrounds this quantitative characterization of the test and evaluation and the quantification of what's going wrong and the implications of that, not just for the system, but for the mission. So like I said, thanks to NSF, AFIT, and the DHS. Hopefully I've answered some of your questions and you would have a question for me or two before we go to the poster if you're joining us.
I don't see any question in the text. Are there any questions right now in the room?
I just want to drink.
If you guys want, you can ask the question at the end of the session, during the poster session. Okay? Okay, thank you everyone.
Thank you, Eric.